Welcome to our NPTEL courses in power electronics, advanced power electronics and control. We shall continue our discussions with the PWM Rectifier II where we have left. So, we are discussing about that actually modulation index will also change like this. So, once actually your input voltage is low, you require to boost up, but you require to maintain some kind of modulation index. So, we require to maintain some kind of minimum modulation index to maintain this thing. So, it should not touch 0 when actually input voltage is at its peak, and we require to do some mechanism that has been listed here, that is to avoid distortion near 0 crossing. The converter should be capable of producing actually this modulation index approaching infinity. So, definitely it is not possible, but we should have, it means that actually the switch should be continuously on close to the 0 crossing. Above expression neglects also the converter dynamics. So, you cannot have this kind of crossing because you require to have a short circuit protection. Short circuit protection will come into the picture and ultimately it will shut it down. And what happened, boost, buck boost, choke, SEPIC and other DC to DC converter with similar conversion ratio are also suitable. These are essentially there are non-isolated DC to DC converter. We also have another type of DC to DC converter, we will be discussing DC to DC converter later. So, these are called isolated DC to DC converter that comes with a high frequency transformer incorporated inside. And we will see that the boost converter exhibits the lowest transition stresses with the switches, and we will discuss the reason for that also. So, let us take the typical DC to DC converter, that is called boost converter. What essentially it does, it boosts up the voltage. What happen, when actually switch is on, this Q1 is on, then essentially this voltage goes 0 and current builds up across it. Since this current builds up across this, so current will ramp on. Thereafter, what happens? This switch will off, and due to that actually there will be a good amount of stress across the switches. We will talk about that stress, and ultimately due to the change in current, LDIdt will come into the picture. So, this voltage plus LDIdt will be basically the charging the capacitor. And what happened in this configuration, this topology is quite easy to use it, and you have this kind of thing and this kind of ripple kind of voltages in the input, and the control will do something. Control will basically will put a hysteresis band, and we shall restrict that current within the hysteresis band. So, ultimately in input side what will happen, you will get actually lot of switching, and this switching will be mitigated by the switching harmonics, and if you can keep this switching frequencies very high, then you can get boosted DC from AC, and power factor and the power quality issues has been solved or addressed totally. Students are actually requested to visit the data sheet of UC 3854 or 55 and so on. So, this data sheet will, and the application note of the Texas Instruments will give you basically the total detail and working principle of this DC to DC converter, thereafter AC to DC and DC to DC converter, where it addresses the power quality issues quite well. The DC output voltage here is actually, since it is a boost topology, it will boost up the voltage. Essentially, you know that in boost topology actually V in 1 minus D is basically the conversion ratio, where D is the duty cycle of the Q1. the output voltage is greater than peak AC input voltage, and the control varies, the duty cycle necessary makes Ig proportional to Vg. Now, variation of the duty cycle in case of the boost rectifier, since it comes with the boost topology. So, you will find that actually this modulation index, if you is basically the ratio of Vt by Vg, and essentially it is V by Vm sin omega t. Since modulation index in case of the boost converter is required to be higher, because it is basically, if you go back, basically you can write actually Vm into In, V0 equal to m into In. So, m is essentially here is 1 minus 1 by d. So, this value is basically more than equal to 1. So, in the boost converter it is required that V is greater than Vm, and if the converter operates in continuous conduction mode, which so we will assume that actually load current little heavy, then only actually process of this conversion require easier and THD get improved, but it is if it is a power, if it consume very low amount of the current, that is really a challenge to the designer to design such converter. So, we assume that it is a continuous conduction mode, and we have 1 by 1 minus dt, and the duty ratio should be therefore follows is equal to 1 minus Vg by V in case of the continuous conduction mode. Similarly, inductor current ripple will be given by del Ig equal to Vm square. So, low frequency average component of the inductor current is given by this, that is basically Vg by Re. So, converter operates in CCM when IGT Ts is greater than actually this delta IGT, and ultimately the corresponding dt which actually makes the converter into a continuous conduction mode is this ratio. So, we have to make the duty cycle such that it is less than 12 by Re Ts, where L is the inductance of this boost converter, Re is the effective or resistance connected to the load, and the Ts is the actually time period of the switching. So, we can substitute here, and substituting that we can get Re is basically, Re should be less than this expression, that is 12 Ts 1 minus Vgt by V, and this system will operate in the continuous conduction mode, and analysis is quite easy in a continuous conduction mode. Once it becomes discontinuous conduction mode, that becomes very difficult to maintain THD. So, for this reason design and required to operate this converter into the continuous conduction mode. So, realization of the near ideal rectifier. So, for this reason this is a condition where you can make current continuous. So, please note that Vg varies with the time between 0 to Vm, hence the equations actually equation may satisfied at some point on the AC line and not at others. So, since this value is changing, the converter always operates in CCM mode provided that this condition has been satisfied, because this you cannot take any guarantee over it, who is higher and who is lower. So, converter always operate in DCM provided that if Re is more than this, Re is between the limits of the converter DCM and CCM nearly to the 0, and it generally makes the transition CCM to DCM. Now, static input characteristics of the boost converter. So, we can model this boost converter as this. So, we have a switch with an inductor. So, that can be modeled at 12 by d square T s. Ultimately, this will be the switching on and the switching off, this will be the power, and this is the actually the Pt by V minus Vg is the current flowing to the system. Now, you see that what happened here, the static input characteristics of the boost converter. You just have a boost converter, that is basically for sake of recall is this, and how you will get this. See, ultimately this ultimately when you short it, so ultimately you got an inductance. So, this has been lumped here, and current flowing into it also basically this point minus this point. So, this is the power minus these voltages. So, thus actually in CCM the boost converter equilibrium, this is basically the normal boost converters duty cycles is, you can equate this actually 12 by Vts into Igt 1 minus Vgt by V equal to d square Vgt by V. Students are requested to go follow the book like Ericsson and others to find the detailed derivation of it. Due to lack of time, actually we cannot go to the all the derivations part of it. The CCM and DCM mode of the boundary in terms of Vg and to Ig can be actually 12 Vts into Ig should be greater than Vg by V into 1 minus Vg by V. From there, so we can solve for the input current. So, input current becomes Vgt by 12 dt square Ts plus Pt V minus Vgt. From there actually you come to the overall expressions of it, that is Pt equal to Vg square T 12 by dt square Ts. So, what we can conclude from this actually data, that is if it is CCM you have very simpler equations, and that is what in a if you have done the courses on the power electronics and you have studied a DC to DC converter, you are aware of the fact that actually the boost converter actually conversion is actually 1 minus D. So, while it is in a discontinuous conduction mode, you can find that 2L Vts Ig 1 minus Vg by Vt, that is this is nothing but actually this expression equal to dt square Vg by V. So, this will govern the equations, and you will find actually this is the expressions of the, this is the expressions for the duty cycle and this is the expressions of the load current. You can find that basically this is the zone, this is zone where it is actually you can find that these currents are discontinuous conduction mode, and till this time it will go to the continuous conduction mode. If duty cycle is quite high, as high as 0.8, so it will come out from the actually the when it is less than actually 0.25 of the duty cycle, so it will come out from the discontinuous conduction mode, and if it is duty cycle is quite low, so it will continue to be discontinuous conduction mode for the larger duration of the time, and thus operation becomes difficult. So, let us consider that open loop DCM approach and with the other approaches. DCM makes actually system less bulky. Why? Basically the failure of the inductance required to be less in case of the DCM. So, and its control is quite simple, you have only voltage control, but disadvantage is that your duty cycle is quite low. So, for this reason what happened, higher peak current, larger EMI EMCs, this problem will pop in. Like other DCM application, this approach is usually restricted to the low power applications, and mostly your mobile charger and the laptop chargers are having these features, and that is quite nasty with respect to this actually EMC, because of the high peaks, because current has to be low, because you are actually in your mobile charger you are basically reducing your voltage to 5 volt from actually 310 volt peak voltages. The boost converter, though it is a buck operation anyway, so boost operation can we find it application mostly in the actually there is a mostly in UPS. Most of the UPS will say that it is power factor corrected UPS. So, in that power factor corrected UPS we incorporate this boost topology. So, after this boost topology we followed by a half bridge inverter that will feed your actually the power to the actually the inverter. So, there is a different kind of inverter comes into the pictures. If it is actually online UPS, what happens there? You actually get it by this method. Otherwise, if there is offline UPS generally supply when power goes out, and also there is a line interactive UPS that also correct the sags. So, if you have actually online UPS, generally it required to be power factor corrected and it shifts out the waveform quite well. And also many adjustable drives nowadays, actually ACs and other applications are coming out with the inverter driven applications, like it should have adjustable speed drive. There also will have this kind of applications, but mostly since ACs wattage, most of the household uses 1.5 ton ACs. So, wattage will be around 1.8 something like 1.8 kilowatt or something like that. So, there what you will find actually since the loading is quite high, it will go to the continuous conduction mode. So, these are the few applications nowadays, because gradually we have we have washing machines that can be also inverter fed, we have ACs also inverter fed. So, all can be have a inverter fed drive, and thus what happened, we require to rectify it and we require a PWM converter place in between to actually give you a process DC to the rectifier and thus a process AC in the output, and also you do not throw any garbages in terms of the power quality to the utility. So, let us come back again, this is application part of it. So, boost converter can also can be operated in DCM as low as the harmonic rectifier, and its input characteristics is given by this. So, that is IGTS equal to Vg by Re plus Vg square Re Vt minus Vg. So, what happened here, in discontinuous conduction mode you cannot get rid of the problem of TSD. Input current contains harmonic. If V is sufficiently larger than Vg, then harmonic will be small. So, that is all about it. So, but it is not the case, generally we have a harmonic issues in the case of the discontinuous conduction mode. So, similar type of approaches can have in CCM mode, and we can have a different kind of topologies. This is basically the Sepik topology, Chuk topology, pronunciation is Chuk, and the buck boost. Chuk is also a kind of buck boost, and also a two switch buck boost topology or any other buck boost topology. And thereafter we may have a isolated conversion, that is flyback, thereafter forward, thereafter push pull, we can have so many things in case of the this conversion process. And boundary or the critical condition mode of operation of boost or other converter at boundary between CCM and the DCM. Buck converter has an advantage, but it makes the distortion occurs, but stresses across the switch will be lower. Another application can be on the resonance converter. So, that is applicable for the 0 voltage or 0 current switching. So, it comes with the actually inductor and capacitor bank, which we have a natural frequency of oscillation that help us to switch either when current across the switch is 0 or the voltage across the switch is 0, and that leads to the 0 voltage or the 0 current switching. Same way this switch can be off when voltage across or the current through the devices is 0. So, same way we can have a 0 turn of losses. So, resonant converter, such parallel resonance converter or some quasi resonance converter can also be used for this purpose. We shall discuss in detail about it subsequent applications. Converter that combine the function of rectifications and also sometimes the energy storage and DC to DC conversion. Mostly this application is a flyback, where actually we have a special kind of transformer. Generally transformer does not store energy. We have a special kind of transformer that is called inductor transformer. Not only will convert, and it also store energy, and it will fly back when it is required in the negative half cycle. So, that is also some other approaches can be followed in case of the PWM rectifier. Now, let us see one example where actually the power flies and it stores the energy, and see that this is a very common usage of below 100 watt AC to DC conversion. Thus, your all laptop charger, your mobile charger essentially of this kind of topology. So, this is the EMI filter. As I told you, it may operate in the discontinuous conduction mode, and thus we have a huge problem of EMI EMC. Since you are using a mobile, so if it also actually interferes with your communication, of course your sound quality of the mobile will deteriorate. So, we require to suppress the conducted emission as well as the radiated, but we cannot do much about this actual radiated emission, but we can reduce something about the conducted emission by putting the EMI filter. So, this is the rectifications, and ultimately we got the DC. Please mind that there is no capacitor, so that we get a double frequency ripple in the output. And this is the MOSFET most of the cases, because power rating of these devices are quite low, and see the dot convention of this actually the topology. You can find that this dot here, then dot is here. Generally in case of the normal transformer, we have a dot here, where actually current try to flows here, actually it will oppose and current will go out, but here dot is actually this position. So, ultimately when switch is on, current flows, no current will flow, and thus this inductor required to be, thus this actually the transformer require a special property, and it required to actually store the energy. So, due to that actually when it will be off, this some portion is omitted, there will be a diode actually to suppress the stress across the switch, and what happened then, there will be a resetting winding. So, it is a simplified oversimplified circuit. So, then actually current will flow back to the secondary. So, you can choose the turns ratio by anything, because you have to have a huge drop in voltage for the mobile or the laptop charger, and thereafter you can also change it by the duty cycle. So, thus the operation in the discontinuous conduction mode, the converter obeys the Ohm's law, and the effective resistance is 2N square L, where L is the leakage inductance, not the EMI filters, leakage inductance of this actually the inductor, by dt square Ts. Hence, simply connect the input port to the AC line, the power will be converted. So, this is the, here you can see that what happened, we have violated two things. This has a storage element. So, we are saying that normal converter should not storage element, input should be equal to output, but here input is stored for a very small fraction of time, and thereafter it will be transferred to the output. and this is a basic advantages. So, since this power flies, so what this is called flyback converter. And so, realization of the actually non-ideal rectifier, let us see that how we can model this isolated DC to DC transformer. Some we require isolation for a highly sensitive device. Of course, you know, if your mobile phone is worth of 30,000, if you can afford, or 50,000. So, you do not want that actually to simple spikes in the inputs your mobile get damaged. So, for this reason, this gives a galvanic isolation from the surges and other voltage stresses, and for this reason actually this isolation has been preferred for your costly sensitive low voltage devices. So, let us come to the design actually the modeling part of this flyback converter. So, you know, same way what we have done, the IG is flowing, and here you know we will change this transformer and switch to the equivalent resistance RE, that value is given by this. So, it is n square to n square L dt square Ts, and power will flow to the secondary, that is Ts, and that will be given by V into IT, that will be equal to R. Please understand that capacitor is placed here to actually smooth out the ripple in case of the DC, but there is no actually input here bulky capacitor in the AC side or the rippled DC side. Under steady state condition operates with a constant D. So, if you have a constant load, but it will change. Why? Because you know I was telling you that these are mobile charging applications. It is a mobile charging application, you have different mode of charging. Initially when mobile actually almost 0% charge, so it will charge in a first charging mode. So, current through this will be high. Since it is a chemical process, you know actually automatically charging will be slow up, and then we will go for the different mode of charging. So, if we assume that a load, it may be actually you are driving the LED for the lighting purpose. So, then you require a constant load, and ultimately you got a constant D maybe. So, adjust D to control average power drawn from the AC line. So, if you wish to change this R, then something will change, otherwise everything can be fixed. Now, there is some issues here, the converter design. So, that is a huge topic of DC to DC converter, but we have to consider it. So, we have told you that to make it in a discontinuous conduction mode, we should select L, a small value, so that DCM operates and occurs through the line, and DCM occurs. So, again in case of that it is a buck operations as I told you, and since D2 you know that actually D VGT by NP. From there we can solve the value of D, and ultimately we will find it out 1 by 1 plus Vg by NV. So, converter operates in discontinuous conduction mode every switching period where above inequality is being satisfied. So, you can see that when switch is on, current will actually picky, you know that is a problem of EMI MC. So, current will actually picks up. This is basically the average current. So, this dotted line. So, ultimately this region, this switch will be on, the inductor will be building the current through it. Thereafter, this will fly back into the secondary for the time period of D2 into Ts through this actually the diode action with the resetting winding. This has been not discussed here for actually simplicity and the time of operation. Thereafter, you know current through this actually diode or the resetting winding decayed, until this time D3 into Ts there is no current into the circuit, and for then that leads to the discontinuous operation. When in the continuous conduction mode actually this should be equal to 0. And to obtain the DCM at all the points of the AC input sinusoidal, the worst case voltage Vg that should be equal to Vm, and inequality is being satisfied. So, this is quite applicable in the application specific case. I shall continue to our discussion in our next class, because for take a single example, you can use your laptop charger in USA where supply voltage is 110, and also in India that is 220 volt. So, how this actually applications fit to this requirement, we shall continue to our discussion. I hope that actually students are finding this discussion in practical examples are quite interesting. Feel free to feedback once you are attending the classes in my mails. Thank you very much for your kind attention.